Hi, I am Shahnawaz. This is the fourth lecture on metric spaces. In this lecture, we will be doing Cauchy sequences in metric spaces. In last lecture, we discussed the notion of convergence in specific metric spaces. So let us consider the notion of convergence in the discrete metric space. So example, let X be a non-empty set. Let D be a discrete metric on X. That is, for any X or Y in X, we have T of xy, it is either 0 when x is equal to y, or it is 1 otherwise. Now let us consider a sequence. Let x and y n is bigger or equal to 1 be a sequence in X, be a sequence in X that converges to X, that converges to some X belongs to X, say X. Now by definition, if we take epsilon equal to half, now for epsilon is equal to 1 by 2, by definition there exists an integer, say n naught, such that then there exists a positive integer say n naught, such that d of xy is less than epsilon, which is in our case half, is less than half whenever n is bigger or equal to n naught. But in the metric space under consideration, d of xy is either 1, otherwise it is 0. So if it is not 1, it has to be equal to 0. But d of xy is less than half if and only if d of x and x, sorry, it is xn over here, is 0. Now by second metric axiom, this implies xn is equal to x for all n bigger than or equal to n naught, if and only if d of xn is equal to 0 for all n bigger or equal to n naught. This further implies this sequence is convergent if and only if this further implies x n is equal to x for all n bigger or equal to n naught. So we have observed in a discrete metric space a sequence converges if it is eventually constant, i.e. if at some finite stage after which the terms of sequences of the sequence eventually become constant, eventually the sequence stabilizes. Now let us consider the space of continuous functions. So now let us consider x to be the space of all continuous functions over the interval closed interval a b, that is the space of all continuous functions on AB. So let us take we know that we have studied earlier that we can define two metrics over here over this space. One is called the uniform metric or supremum metric, and the other one is integral metric. Define for all continuous functions f and g in x, which is in our case CAB. Define for all f and g in x d of f comma g to be the integral metric, i.e. is integral a to b absolute value of difference of fx and gx dx. Now a sequence of function in x converges in x. So let us consider a sequence fn where n is bigger or equal to 1 in x converges to some f in x as if and only if limit n goes to infinity, distance between fn and f, that is equal limit n goes to infinity integral a to b mod of fx minus gx dx, this is equal to 0. Now note that in this metric space with this metric integral metric, the convergence doesn't imply the point-wise convergence, as in previous examples we have seen that the convergence imply point-wise convergence, but in this example in this space convergence doesn't imply point-wise convergence. So let us do one example here. the convergence in CAB with respect to above metric does not imply pointwise convergence. So let us do one example. Solution. Take a is equal to 0 and b is equal to 1, i.e. the space of all continuous functions over the closed interval ab. Let us consider fx to be the constant function 1 for all x belongs to 0 1, and define a sequence like this. And define f and x, this sequence over here, to be nx whenever this x lies between 0 and 1 over n, and 1 otherwise. So if we take if we sorry this is over x and this is over y axis, huh? Now our interval is 0 1. Let us take 0 here and 1 here. Now for n equal to 1, f1 of x will be x. So this n here is here equal to what? It is equal to 1 here. So our function will be like this when n is 1. So this will be the point 1 1, and this will be the graph of the function f of 1. Now when n is equal to 2, this will be 2x here, so the slope will be double, but this function f2 will behave as 2x when x varies between 1 and half. So if it is half here, so slope will be double. So at half, so it is here 2 at half, the value of f2 will be equal to 1 at half. So between 0 and half, the function behaves like 2x. So the graph will be like this. So this is point half 1, and between the interval half and 1, it will behave as a constant. So it is like this. So this is our f2. Similarly, when n is equal to 3, So function will behave like 3x over the interval 0 to 1/3. So if it is 1/3 here, function will be like this. So f of 2, we'll write f2 here. So for f3 it will be like this. And for the interval 1/3 to 1, it will behave like 1. So this is our f3, and the sequence goes on like this. So let us label this as figure A. So the functions fn are illustrated in figure A. Now d of f and f, this is integral 0 to 1 mod of f and x minus fx dx. So this will be equal to, now this will be like 0 to 1 over n, it is f and x minus fx plus 1 over n to 1 mod of f and x minus fx dx. Now between 0 and 1 over n, or fn is, or f and x is nx, and this is 1 dx, plus between 1 and n1, fx is 1 and fx is 1. So this is 0, this term over here. Now we can write this as one minus nx dx. Now this function 1 minus 1x is non-negative over the interval 0 and 1 by n. So we do not need this absolute value here, as a function is non-negative. So this is equal to 0 1 by n, 1 minus nx dx. Let us integrate it. We get, this is x minus nx square over 2, and the limit is goes from 0 to 1 by n. So this is equal to 1 by n minus 1 by 2n. Hmm. 1 by 2n. Minus 0. When we put 0 here and here, this becomes 0. So this is equal to 1 or 2n. Now note that as n goes to infinity, this term over here becomes 0. So limit n goes to infinity d of f and f, it is same as limit n goes to infinity 1 or 2n, and which is equal to 0. So we can say that this sequence fn converges to f. Now to check whether this convergence is pointwise or not, note that fn of 0. Now if we take fn of 0, so 0 falls in this interval, so it is 0 over this interval. So fn of 0 will be 0 for all n, while f of 0, but f is chosen to be equal to 1, i.e. the constant function, so f of 0 is equal to 1. So this fact over here confirms that the convergence is not pointwise, so that fn does not converge to f pointwise in the interval 0, 1. Now let us define now Cauchy sequences. Now we have Cauchy sequences. So let us define first what a Cauchy sequence is in a metric space. So we have definition. Let XD be a metric space. A sequence xn, where this n is bigger or equal to 1, in the set X is said to be a Cauchy sequence, is said to be a Cauchy sequence if for any given positive real number, if for every epsilon positive, there exists a natural number, there exists a natural number say n naught, such that distance between any two terms of the sequence, say xn and xm, becomes less than epsilon when n and m are both bigger than or equal to n naught, i.e. distance between the terms xn and xm of the sequence, it becomes less than epsilon whenever these two terms are chosen from the sequence after n and m. After n and m are both bigger or equal to n naught. So let us make a remark here. See, a sequence xn in the set of real numbers or the set of complex numbers is a Cauchy sequence in the sense familiar from elementary analysis, i.e. if and only if it is a Cauchy sequence according to the definition above, in the sense of usual metric on R or C, where R and C are real or complex numbers respectively. So a sequence xn in R or C is a Cauchy sequence, if and only if it is a Cauchy sequence, it is a Cauchy sequence according to above definition. According to the definition given above. In the sense of usual metric, in the sense of usual metric on R or C. Note that a convergence sequence in a metric space is always a Cauchy sequence. So let us do a proposition here. A convergent sequence in a metric space is a Cauchy sequence. Proof. Let us consider, let XD be a metric space. And let us consider a sequence xn to be a convergent sequence in X. Be a convergent sequence in X, converging to say X in X such that the sequence converges to x, where this x is in x. Now by definition, for any epsilon positive, there exists some natural number, say n naught, such that distance between any term of the sequence xn from x becomes less than epsilon whenever n surpasses n naught. So therefore by definition, given any epsilon positive, there exists a natural number, say n naught, such that distance of the term x n of the sequence and this limit of the sequence x, it becomes less than epsilon. So this is another epsilon here, whenever this n surpasses n naught. Let m greater or equal to n naught be any natural number. Then by this definition over here, then distance between xm and x, it is also less than, say, epsilon by 2. Now d of distance between the terms xn and xm, using triangular inequality, it is less or equal to distance of xn and x plus distance of xn, xm and x. So actually it is d of xxm, but by the third metric action by symmetry, it becomes d of xmx. So this is further less than epsilon by 2 over here. Plus this is again less than epsilon by 2, but it is true whenever n and m they surpasses n naught. So this is equal to epsilon. So this becomes the definition of Cauchy sequence. So distance between two terms xn and xm, it becomes less than epsilon whenever there exists some stage say n naught, after which this distance becomes strictly less than epsilon. So hence xn is a Cauchy sequence. Now it is natural to ask whether every Cauchy sequence in a metric space is convergent or not, but the answer is no. Let us consider an example. The converse of above result is not true. The converse of above result is not true. So we have to counter, we have to give a counter example. So we have to cook up an example of a Cauchy sequence in a metric space which is not convergent there, i.e. which converges to some point outside of that space. Solution. Now what is the solution? Let us consider x to be the set of all rational numbers with the usual metric on R, or let x be the set of all rational numbers with the usual metric. Namely d of xy is nothing but the absolute value of difference of x and y for all x and y in x. So now what we need to do is we have to cook up a sequence which is Cauchy but not convergent. So let 1, 1.4, 1.41, 1.414, so on, be a sequence in Xn. Note that it's a Cauchy sequence. So if we compute the difference between these two terms, it is equal to 0.01. Between these 2 points, it is equal to 0.004. So difference between the consecutive terms or any two terms, it becomes small. So it is a Cauchy sequence, and it converges to be a sequence in X which converges to root 2. Now root 2, this is a point which is not in the space, which is missing from the space. So if it converges to root 2, it implies that this sequence is a Cauchy sequence. But this root 2 not being in the space, that makes it divergent. Not divergent, that makes it a non-convergent sequence. It is therefore a Cauchy sequence. However, it does not converge to a point of X. However, it does not converge to a point of X. So a Cauchy sequence need not be convergent. So Cauchy sequence need not be convergent. We can provide, so this example is a trivial one. We can provide a non-trivial example where we can show a Cauchy sequence that a Cauchy sequence in a metric space that does not converge to a point of the space. So let us take another example here. So now let x be the set of all continuous functions over the closed interval 0 1 with metric d with the integral metric with metric d defined by so d of f and g, that is equal integral 0 to 1 mod of f of x minus g of x dx, where this f and g, they are the elements of this space C01. Now let us consider a sequence. Let fn be a sequence in C01 defined by fn of x. Let us take it to be equal to say 0 when this x lies between 0 and 1 by 2 minus 1 by n. Let us take it equal to be n times x minus 1 over 2 plus 1 when this x lies between 1 by 2 minus 1 over n is less than x is less or equal to say half, and it is equal to 1 when in the other half interval. So note that, observe over here, if n is equal to 1, so this is not well defined. So for this sequence is defined when n is bigger or equal to 2. So one can see that if we take any value of n, the resultant function will be a continuous function. So to illustrate these functions graphically, let us consider the system, Cartesian coordinate system. So it is 0 over here, and let us take this is 1 over here, and this is half. So for any value of n, the nth term in the sequence, if we take any value of n over here, that function behaves constant in this half interval. So at half, this is equal to 1. So to check continuity at half, all we need to do is we have to give 1 by 2 over here, that becomes 0 over here, and this is 1 here. So at this interval, in this interval, it is again 1 here. So at half it is 1, and it behaves constant in this half interval. Now within this interval, this function behaves linearly, and so this has slope so this becomes 0 over here. So this is our point 1 by 2 minus 1 by n. So when we give x is equal to 1 by 2 minus 1 by n, so this becomes n into 1 by 2 minus 1 by n minus 1 by 2 plus 1. So 1 by 2 goes, this n and n goes, and this minus n plus 1 goes, so it is 0 over here. So this is the interval 1 by 2 minus 1 to 1. So in this interval this behaves like this, and in the rest of the interval it is again 0, so it behaves like this. So this is over fn. Now let us consider another function fm, where this m is bigger than this. Let us take m to be less than n. So if m is less than n in this interval 1 by 2 minus 1 by m and 1 by 2, so this will have slope m. Now m is less than n, so this function will have slope less than n, so this will be like this. So this is f of m. Now in this interval it behaves same as the previous function fn. Now this point over here, this is 1 by 2 minus 1 by m. Now since m is less than n, 1 by m will be bigger than 1 by n. So 1 by 2 minus 1 by m is smaller than 1 by 2 minus 1 by n. That is why this point is over here, not here. So this is our function here. So this will be f of m. Now we have studied that this integral norm, this integral metric gives the major gives the area bounded by two functions. So this area over here, this is our d of fn and fm. Now these are fixed, n and m are fixed, so these are two functions. So distance between these two functions gives us the area bounded by these two functions, fn and fm. So what we have observed is that this sequence fn, this is a sequence of continuous functions. So this sequence belongs to C0 1. Clearly this sequence fn, where n is bigger or equal to 2, is a sequence of continuous functions, and hence is a sequence in C0 1. Moreover, it's a Cauchy sequence. Now to prove that, let us proceed as follows. Moreover, it is a Cauchy sequence. Since d of fm comma fn, this is equal to integral 0 to 1 norm of mod of fn minus fm x and dx. So this will be less or equal 0 to 1 mod of f n x plus mod of fmx dx. Now note that this sequence is a sequence of non-negative functions. We don't need this absolute value over here, so this is same as integral 0 to 1 fnx. Let us take m here and n here. This is n, this is m here, mx dx plus integral 0 to 1 fnx dx. Now let us solve one of these integrals and see, and the result will be same for the other integral. Now integral 0 to 1 fnx dx. This is same as integral 0 to 1 by 2 minus 1 by n fnx dx plus integral 1 by 2 minus 1 by n 1 by 2. This will be fx dx plus this will be integral 1 by 2 and 1 fnx dx. So over this interval 0 to 1 by 2 minus 1 by n, fnx is 0. So this will be equal to, now if we combine these two integrals over here, so let us do as follows. Let us erase this thing and take 1 here. So over this interval 0 to 1 by 2 minus 1 by n, fnx is 0. So this thing over here is 0. So this is same as integral 1 by 2 minus 1 by n over 1 sorry, let us keep it like that. So this will be 0, this will be 1 by 2 minus 1 by n, is 1 by 2 here, and in this interval function behaves like this. So it is n times x minus 1 by 2 plus 1. So it is n times x minus 1 by 2 plus 1, it is dx here, plus, so in this interval function behaves as a constant. So this will be this will be half, this will be half, because if we evaluate it, this is integral, this is integral half to 1 dx, and that is half. Now to prove it, we proceed as To evaluate this integral, we proceed as follows. So this is integral half minus 1 by n to half. So this will be nx dx, then it will be minus n over 2 integral half minus 1 by n and half. So this will be dx plus integral half minus 1 by n and half over here. This is dx and plus half. So this is same as nx square over 2. Limits are from 1 to minus 1 half minus 1 over n to 1 half minus n by 2 times x. Limits are from 1 by 2 minus 1 over n to half plus x. Limits are from 1 by 2 minus 1 by n to half plus 1 over 2. Now this is same as on putting values, this is same as this is same as n over 2 and 1 by 2 square minus one over 2 minus 1 over n square minus n by 2 1 over 2 minus 1 over 2 plus 1 over n plus 1 over 2 minus 1 over 2 plus 1 over n plus half. So this is same as n over 2 1 over 4 minus 1 over 4 minus 1 over n square plus 1 over n. Now this is same as minus n over 4. Now this minus, so this half and half goes, so this is minus n over 2 into 1 over n, that is minus n and n goes, n over here, this n and n goes, this becomes minus 1 over 2, this 1 over 2 and 1 over 2 goes, this is 1 over 4 here, plus 1 over 4 and plus half. Now this half and half goes, this 1 over 4 and 1 over 4 goes. Now this is same as n over 2 into minus 1 over n square, this is minus 1 over 2n plus 1 over 2 plus 1 over n. So this is same as 1 over 2 n plus 1 over 2. Similarly, integral 0 to 1 fmx dx. This will be equal to 1 over 2m plus half. So d of fm and fn, this is less or equal to integral of this plus integral of this, that is same as 1 over 2n plus half minus minus 1 over 2n minus half. So this is equal to 1 over 2 times 1 over m plus 1 over n. So if m and n goes to infinity, d of fm comma fn, this will become 0. Now suppose on contrary that this sequence of functions converges to a continuous function. Suppose, so this proves here that this sequence is Cauchy sequence, because this is Cauchy. Suppose that there is a continuous function this is a continuous function, say f such that this sequence f and converges to f such that, let us write it as follows, such that d of f and f tends to 0. Now doing so, we must get a contradiction. So if it is true, then d of f and comma f, this is equal to integral 0 to 1 f and x minus fx dx. So this is equal to integral 0 to 1 by 2 minus 1 by n f and x minus fx plus dx plus integral 1 by 2 minus 1 by n 1 by 2 f and x minus fx dx plus integral 1 by 2 1 by n f and x minus fx dx. Now as so this is equal to, so over this interval this f and x is 0, so this will become 0 to 1 by 2 minus 1 by n mod of fx dx plus 1 by 2 minus 1 by n 1 by 2. Let us keep it as it is. So this is f and x minus fx dx plus over this interval half to 1, so this is 1 here. This f and x is equal to 1, so this will be equal to 1 minus fx dx. Now as n approaches to 0, this will become 0 to half, this will become half to half, so this integral vanishes, so this becomes half to 1. So and since we have assumed that fn converges to f where f is continuous, so d of fn and f, this must tend to 0 as n goes to infinity. So on taking limit n goes to infinity on both sides, we get 0 is equal to integral 0 to half mod of ff(x) dx plus integral half to 1 minus fx dx. Now this term is non-negative, this term is non-negative, and their sum is 0. So this term is 0, this term has to be must be equal to 0, and this term is also equal to 0. This implies uh, 0 to 1 by 2 fx dx is equal to 0, and integral half to 1 minus fx dx, this is equal to 0. Now f being continuous, this further implies now integral is 0 given that f is continuous, so f has to be equal to 0. Similarly over here, given that integral is equal to 0, so this expression over here 1 minus fx, it has to be equal to 0. This implies this fx is 0 over the interval 0 is less or equal to x is less or equal to half, and over this interval when we get this integral over here to be equal to 0, so it forces 1 minus fx to be equal to 0, and that implies f of x is equal to 1 over the interval half and 1. So this is equal to 1 over the interval half and 1. So note that this function is like this. So this is 0, this is 1 here, so this is half. So between 0 and half it is equal to 0. So and between half and 1 it is equal to 1. Obviously f is not continuous, but at the first place we have assumed f to be continuous, so this is a contradiction. So this sequence is a Cauchy sequence but not convergent. Which is not possible, which is not possible since f was chosen to be continuous. Hence a contradiction. Thus the metric space in which Cauchy thus the metric space thus this sequence fn where this n is bigger or equal to 2 is not convergent. Is not convergent. So I think this is it for today. Let us see you in the next lecture. Thank you so much.